Hel-
Blaise, he's going to tell us about Quantile.
Hi, hello everyone. Thanks, Guillaume, for organizing this summer school and for inviting me. I hope you are not too tired. So I will give 1 hour 30 today and 1 hour 30 tomorrow. Everything will be related to quantiles. I'm not so sure what optimization conscious econometrics mean. But I know what I do and what I like, and Guillaume invited me, so I will talk about what I like. And I'm pretty sure, I hope you will be interested, and hopefully you will be interested too. So I will just start by the question, why do we use quantile regression? Because we got an introduction this morning, and so just wanted quick historical, a little look at the history and why people are using quantile regression. Then I will give a few examples of the most common errors you can do in constructing quantile models, and which is, I can give a spoiler, which is to implicitly assume that the quantile operator is a linear operator. And I will give many examples of that. And one of them is the difference between conditional and unconditional quantile treatment effects. And because you can use quantile regression to estimate conditional quantile treatment effects, I will talk how you can estimate unconditional quantile treatment effects. We'll give usual results about estimation, algorithm, asymptotic distribution. And then we'll compare these two sorts of estimates. And to conclude, I will also compare with unconditional quantile regression, which is still a different method suggested by Firpo, Fortin, and Lemieux. Okay, so let's start. Historically, quantile regression has been introduced, invented, discovered, I don't know what is the right word, by Kanker and Bassett in a paper in Econometrica in 1978. And in this paper, and in the first papers, they have written in this period, let's say, end of the 70s, during 80s, actually the main reason to use quantile regression, the main reason they give to use quantile regression is the robustness. So they put that in the robust statistic literature, like people like Huber, Ampel, and actually they're assuming that the model is homogeneous in the sense that they're assuming that y is a linear function of x plus an independent error term, and we want to estimate this parameter. And we can do that with OLS, or with a trimmed least squares like Huber was suggesting, or using least absolute deviation, which is median regression. Okay? And they were comparing efficiency with outliers, things like that. But actually, today, if people are using quantile regression, it's not for that, but it's to study the heterogeneity of the effects. And here, during the 90s, you have a paper, I'm sure that Guillaume mentioned it, by Gary Chamberlain, where he used quantile regression to study the effect of being member of a union on the distribution of wages. And he especially used quantile regression to show that the union will compress the income distribution. Okay? And to show that, you need to allow for the heterogeneity of the effect. Okay? And starting from that, then with his student Moshe Bushinsky, written a few influential papers in Econometrica in particular, then people have used quantile regression to study this heterogeneity, and I would say that today 95% of the application of quantile regression are to study this heterogeneity. So if you take the classic, so just a notation, introduce a notation, here I separate the intercept and the regressors, and you will see why in a few seconds. So what is important is that we want to allow the coefficient, the return, like if this is characteristic, this will be the return on this characteristic. We allow it to be a function of tau. So we want to allow it to change with tau. While if you have what I call homogeneous regression model, where you have an error term which is independent of the regressor, then if you have such a model, which is also a classical linear regression model, where like epsilon is normally distributed and homoscedastic, then this model will imply that beta tau is constant as a function of tau. So if you just show generated data, if you have homogeneity, then all quantile regression lines will be parallel. Okay? So there is no reason to use quantile regression in some sense because OLS will give the same slope. Only the intercept will change with the quantile index. Yeah, like I said, the only reason will be the robustness or efficiency. Because if you have fat tails, then median regression or another quantile regression may be more robust and may be more efficient, so will be more robust and may be more efficient than OLS. But it starts to be more interesting when you have something like here, the simplest case, the heteroscedasticity, where you see that the variance of y is increasing in x, and then the slope is changing with the quantile. And this is the sort of thing that we want to analyze with quantile regression. For instance, if what people typically do, they plot the slope as a function of the index. So you put the quantile index on the x variable, and you put the slope on the y variable as a y variable, and then you will see here in such a case that the slope is increasing with the quantile, which means that if x increases, the variance increases. Okay. So actually, if you plot real data, if you put education or experience, you get something like that, and the wage, like a Mincer equation. You get something like that. And you have actually theoretical reason why it would be the case. Let's take experience, or let's age or experience. Then when you enter into the market, the firms has not much information about your ability. So the wage will be based on your CV, where you have studied and things like that, but different students coming from the same, with the same, from same university, let's say, they will be very similar, and so firms will not give very different wages. But with the years, the firms will learn about your productivity, your individual productivity, and so the dispersion will increase because of that. Okay. So you have model predicting that, and then you look at the data and you find that. So it's something that we definitively want to allow. Okay, so it was just his first point, and the goal was to explain what I call an homogeneous and heterogeneous model. The heterogeneity is heterogeneity in the slope beta tau as a function of tau. If it's flat, if it's constant, or if it changes with tau. Okay, so now let's come to the second point. Like I say, the main mistake you can do when you try to modelize a quantile, so you want to modelize a quantile of y, and it is assuming that quantile operator is a linear operator. So I'm pretty sure Guillaume did that this morning. I could not attend. But in his book, it's what he's doing. And I am doing the same when I teach. It's very natural to do that, is to explain, well, you know OLS. With OLS, you estimate a conditional expected value of y given x. Now I will introduce a new method, it's quantile regression. We will estimate the conditional quantile of y given x. And then they look very similar. Okay? And it works well in the linear model, but there will be cases where actually it does not work so well. And then many of the mistakes that have been done in the literature are really to do something with quantile regression that we did with OLS, and it did not work. It does not work in all cases. And the reason is that the quantile operator is not a linear operator. What I mean is that the quantile, so tau is a quantile index, a number between 0 and 1. Quantile of the sum is not the sum of the quantile. So it's completely, I mean, when you think about it, it's obvious, but it's easy to make the mistake. And this, of course, implies that there is no law of iterated quantile. So you can try, so if you try to find a relationship between the unconditional quantile and the conditional quantile, you can try the expected value, you can try a quantile, same index, different index. Nothing will work. Okay? So there is not a function mapping the conditional tau quantile to the unconditional tau quantile. And the topic today is to see what we can do to map, and what we need actually is a full quantile function for all tau from 0 to 1, and then there is a mapping. You also need the description of x, but then there is a mapping from this conditional quantile to the unconditional quantile. Okay, this will be a main topic of today, but before we do that, let's see, okay, this is the first bullet point on this slide, but I want to give a few examples of things you can do. Yes, sorry, Guillaume.
Just for motivation, so the idea is we want the unconditional quantile, but we're starting with the conditional quantile for reasons of accuracy.
Okay, I will come in a few slides. It's if you have a treatment, then the thing is, I will be assuming conditional independence, so I need to condition x. to make the treatment as good as possible exogenous, but then I'm interested in the unconditional quantile treatment effect for ease of interpretation. Okay. So this will be the motivation. Okay, so first example, I will talk about it today. Second example is, so the first three examples I will cover today and tomorrow. I mean, the third one, I will not have much time, but I will try to cover them. So the first one I will cover in details today. Second one will be double machine learning. You know, if you want to make inference after model selection, you have different methods. I will talk tomorrow about results by Chernobyzov and co-authors. For instance, you have double selection or double machine learning. If you apply this method in a naive way, it will not work. Like, you know, double selection is you regress y on x, and you also regress d on x, and then you use a union of the selected variable. Let's say you lasso, and use a union. If you do that with quantile regression, it will not work. And I will explain why tomorrow. It's related to the bias, which is weighted by a density. And so you have to weight with the density when you do these two regressions. Okay. So I will say more tomorrow, but it's a second example where if you do the naive thing that, I mean, if you do naively the thing that you are doing for the mean regression, we do for quantile regression, it does not work. Panel data, if you, with fixed effects, okay, if you first difference all y and x, then you will change the parameter that you are estimating. Okay? So you know with OLS, you can, let's say you have two time periods. You can first difference, or you can time demean, or you can estimate dummy variables. They are all numerically identical with two time periods. With more than two first differences and the fixed effect of the time demeaning, they give numerically different parameters, estimates, but they will converge to the same value. It's quantile regression, there is no reason it's the case. First difference does not work because you get the quantiles of the changes, and which is not the parameter that most of the time you are interested in. And then explicitly estimating fixed effects, you have an incidental parameter bias, again, not a linear operator, which means that the fixed effect does not cancel. I mean. So I hope I will have time to say a few words about that. Then I've given other example, a very simple one, measurement error in y. You know that if you have measurement error in y and you estimate OLS, it's not a problem. I mean, if the measurement error is a classical measurement error, you just go into the error term and it's fine. With quantile regression, it's not fine. It will bias the result because you are adding noise to the depending variable, and so you don't know what is the original, the structural noise and the measurement error noise. They are mixed. There is a paper here, Hausmann, Liu, and Palmer in Econometrica, suggesting one solution. I'm not sure it's the end of the story, but it's a discussion of this point. Instrumental variables. Again, OLS, so mean regression, you can use a fitted value approach, like two-stage least squares. You can use a control variable approach. You can use a world estimator. They all give us numerically the same solution. Now with quantile regression, if you naively apply two-stage least square and you do two-stage quantile regression, it will work only if the effects are homogeneous, like if beta tau is equal to beta. Some people have tried that. It does not work. I mean, you get results. This is the problem, but it does not estimate what you want to estimate. A naive control variable approach also does not work. A paper by Simon Lee, beginning of 2000, I don't remember which year, in Journal of Econometrics, implicitly somewhere hidden is the assumption that the effect is homogeneous. Okay. That makes no sense to estimate quantile regression. So here there are two solutions depending on where you want to impose assumptions. If you want to impose a monotonicity assumption, like Angrist-Imbens type of monotonicity assumption, then you can estimate quantile regression with an instrumental variable. It's a paper in 2002 in Econometrica. If instead you want to impose a restriction on the outcome equation, which is a rank similarity assumption, then you have Chernobyzov-Hansen. These are consistent. The first naive two are not. Control variable approach also, if you want to do it for sample selection, it will not work like Heckman style sample selection. You estimate inverse Mills ratio, then you have a non-parametric or semi-parametric version of it by Whitney and Huey, where you have a series. You have a series in the inverse Mills ratio to control for the sample selection bias. If you do the same for quantile regression, it will work only if the effect is homogeneous. Actually, it's what Moshe Bushinsky has proposed in a paper, Journal of Applied Econometrics, 98. He got the prize for the best paper in the last 2 years. And actually, the paper is wrong. Because he's assuming that the error term is independent of x, but then later in the application, he got different coefficients across quantile, and he interprets these differences and said they are significant. By showing that the difference between that beta as a function of tau is not constant, is showing that the model is not valid. So you cannot do that, and if you want to find a solution, there is one in Arellano and Bonhomme, where they need to impose additional assumption. What they do, they restrict the copula between the error term in the selection and outcome equation. Okay? So they assume it coming from a known family, and then you can estimate the parameter of this copula. So this one is consistent, the previous one is not. With difference in differences, it's a little bit more, so less clear, but I think a naive quantile difference in differences is not attractive. Okay? So it's discussed in a very nice paper by Atten and Emmons. If you don't know it, you should definitely read it. They suggest another model they call the changes in changes. And compared to the changes in changes, doing naive quantile difference in differences, which means that you take the diff equation, but you estimate with quantile regression instead of OLS. I mean, in principle, it's possible that it's a model that is not necessarily self-contradictory, but it assumes additive separability of the time effect, which is very unnatural for quantile models. And it's not equivalent with respect to strictly monotone transformation. What is meant here is that if you do diff in level, and then diff in log, you may get like positive effect in level and negative in log. It's possible with mean regression, and it's possible with this quantile difference in differences. And one of the big arguments in favor of quantiles is that there are equivalents with respect to strictly monotone transformation. So, yeah, it's the last square point here, is that they have good things. Okay? There is one difficult thing, which is it's not linear, but they have good things. And one of them is that they are equivalent with respect to strictly monotone transformation. What is meant is if you take the quantile of the log or the log of the quantile, you get the same result. For instance, to give one example. And it's the case of the changes in changes of Atten and Emmons, but it's not the case of this naive quantile diff in diff, which I will not recommend. And finally, and actually I will say a few words about that, if you do a decomposition, like in discrimination studies or Aka-blinder decomposition, if you replace OLS with quantile regression coefficient, you don't get something that can be interpreted. But I will show you today something that can be interpreted. Okay, so this was actually just a short list of mistakes that you should try to avoid and that are very easy to do. But now I will start with the main topic of the lecture today, which is this unconditional quantile treatment effects. So I don't know if you have questions about this first part. Yes? So actually, I was preparing the slide and was not sure what is best. It's pure notation. So so here I think is that it's the only thing that should hit here. So this is a tau quantile of what is inside of the parenthesis, and then we will consider both changing tau and considering different numbers here. Some papers are using one notation, some papers the other. I think I took the notation from your book. So I try. But yeah, you can find. So I was hoping he would use the same in his slides.
Yeah,
okay.
It works well for your point about conditional iterative expectation.
Sorry, you?
It works well for the point about the iterative expectation.
Yeah. Yeah. No.
I think it's great notation, personally.
No. I did not take it like that. I mean, I really try to think about that. What is best? At the end, it's notation. Yes?
Can you go to the scatter plot, please?
Yes.
Yeah. So in the sense of OLS, this will be a problem of violation of homoscedasticity.
Yes.
But with quantile regression, this wouldn't be an issue.
No, but okay. So first, my point of view, it's not a problem for OLS. It's a problem maybe for some standard errors that do not allow for heteroscedasticity. OLS is fine. OLS, here, when all conditional quantiles are linear in X, then also the expected value is linear in X, you get by integrating. And so here OLS is fine. And actually it's symmetric, so the median OLS would be exactly like the median regression. But the point is more that if you have independent errors which imply homoscedasticity, then quantile regression is not very interesting. It's more the point of these two slides is to say, if you are here, quantile regression is not interesting. If you are here, it's more interesting. So you don't want to have a model that imposes that. Now, if the data are like that, still to learn that they are like that, you need a method, and quantile regression may be a method to know about that. But if your model imposes that, and then if your model gives biased results, if you are not in this case, then it's a problem. Yes, okay. So to start with the unconditional quantile regression thing. Well, actually, it's the same vein as what I said before. Let's first consider the randomized treatment D. Okay, unconditionally randomized. Okay. So in principle, here we don't need the regressors. We have regressor x1 and x2, and we are interested in the effect of this randomized treatment D. If in such a case, because D is independent of x1 and x2, if you run the OLS segregation of y only on D, of course, always the intercept, but on y, of y and on D, or you run the regression of y on D and x1, which is the first set of regressor, or y on D, x1 and x2, asymptotically, the coefficient on D will converge to the same value in all cases. It's sort of trivial if you think about the omitted variable bias formula. D and X are not correlated, so the omitted variable bias is 0. So in all cases, you get the same coefficient. If you think the intuition, or if I were to see the Frisch-Vaux theorem, then when you regress D on X1 and X2, you get the same fitted values as if you don't regress D. And finally, if you think in terms of conditional average treatment effect, if you take the average of the conditional average treatment effect, then you get the unconditional average treatment effect. So actually, in these cases, you are estimating the same thing. So if you have unconditional or conditional effect, on average, you estimate the same thing with OLS. Yeah, like you already know with quantile regression, this does not apply. Now, why do you want to add control variables in OLS? You want to reduce the variance. Okay? So if these variables x1 and x2, they have an exponential power on y, then adding these variables will reduce the standard errors. So you see very often applied papers showing first the regression on one, first showing the regression only on two treatments, and then adding variables try to get shorter confidence intervals. And so the temptation, of course, is to do the same for quantile regression, but it does not work. It's not true. When you add control variables, even if they are independent of t, you are changing what you are estimating. So with quantile regression, you get conditional quantile treatment effects, and this coefficient depends on the set of control variables, even if they are independent of the variable of interest. So you cannot play the same game. Okay. Yes?
Are we thinking of well-specified linear?
Yes.
So, so how does it? That's kind of mind-boggling. So it's
Okay. Wait. Well specified. Yeah. It's not about misspecification. Well, and
so the effect is independent and additive, but it changes if we add.
Yes, you can. I mean,
Yeah.
you may have. If you simulate data, not too pathological, there will be similar. But think about what you have. I mean, the paper Angris Chanuzukov Fernandez. They have an omitted variable bias.
Yeah.
It's weighted by the density. So there is no reason that this omitted variable bias is zero. Yeah, let me check.
I guess I'm like stuck in the OLS situation because I'm thinking the effect is additive. Then if I take if it's d1 beta d plus x1 beta x1, and then I don't put in the x1, and that changes the beta d. Yeah, I guess we're so used to OLS intuition, but it is kind of shocking.
But yes. But okay, so it's actually when you think differently, it's not shocking at all.
Okay.
So
yeah, that's what I want.
So let's say one of these variables is, so you have experience and education.
Yeah.
Here, if you regress y on the intercept on d, and let's say you look at 0.9 quantile, top of the distribution, and y is the income, so it means you are the top 10% of the unconditional distribution. Now let's say that you take an individual has a very high level of education, high level of experience, but given this characteristic, her wage is not so high. Maybe below the conditional median. But this person is still at the top of the unconditional distribution. So this person will contribute here to the 0.9 quantile treatment effect, but maybe here to the 0.4 quantile treatment effect. So when we change the conditioning set, we change the definition of the rank. And so we can get different results.
You change the spread at every d, so how that affects the slope on d.
Yeah.
Okay, I see.
Yes.
But when you were showing the two graphs, the heteroscedasticity and the heteroscedasticity, I mean, we could just add like a variable to reduce the heteroscedasticity, which is not correlated with the treatment effect, and this will change the slopes one time. That's basically it.
Okay, so you are saying maybe there is a variable that would capture heteroscedasticity and then.
Yeah. So yes, basically.
Yeah.
It's an example.
Yeah.
That by adding H2, it's not correlated with the treatment, but if it reduces the heteroscedasticity at the at large values of X, you will change the value of the quantile.
Yeah. Probably you are right. Because that if it's not correlated with D, so but yeah, I think you're right. Yeah. No, you're right. Yeah. But what I was saying, the example I was saying is, if you take someone here below the median of the conditional distribution, but clearly above the median of the unconditional one, and so if you think as averaging these individual effects, so let's say that the treatment, then this person will contribute to below the median conditional quantile treatment effects and above the median unconditional quantile treatment effects. Okay. Yes.
Can I ask, so it's scary if it's possible that the treatment effect is found to be significant, say, with the X but not without the X. But here you're just saying that the quantiles change. Are you also saying that the significance of the effect will change?
Yes, I'm saying that. But if you take the integral over all quantiles, you get the average. And here we know by the OLS result that the average does not change. So it's just which quantile is significant and which quantile is not significant may change. But not if you have a uniform test, you have a functional inference, you may not be wrong. You will not be wrong in both cases. But if you consider one quantile, you may get different results, yes. Okay, so what can we do? And one solution is to look at these unconditional effects, but to use x's in the estimation. Okay. So now I want to generalize the previous result. I don't want to assume that the treatment is randomized, but if it is, it will still work, of course. So, but to have a better notation, I still consider binary treatment, and I introduce the Neyman moving potential outcomes y0, y1. In principle, it works also if the treatment is continuous. You have to do, we will see what you can do if you have a continuous variable of interest. Okay, so you have this potential, but it's simpler if you have this binary. You have this potential outcome, and now we are interested in the unconditional quantitative effect, which is the difference between the tau quantile of y1 and tau quantile of y0. We could do that for the treated, okay? So we could have the tau quantile treatment effect. Well, here, sorry for the notation. Should be a subscript, okay? Okay, so yeah, so here it's for the whole population. So the idea is, what would be the tau quantile if everyone is treated? What would be the tau quantile if nobody is treated? And we take the difference between the two as a way to summarize the effect on this unconditional distribution. But like I said, you could do that for the treated, you could do that for the control, you could do that for another population. We will see how it works. Now the observation rule, of course, you observe only one of y1, y0. If d is 0, you observe y0. If d is 1, you observe y1. And here we are assuming conditional independence assumption. It has many different names in the literature. And this assumption is, so what we are assuming is that given x, so here we need x, we need these control variables, so it's why we cannot just do a quantile regulation of y on a constant and d. We will need in some way to find a way to integrate x. So we are assuming that given x, d is independent of both potential outcomes. So this is very common assumption. Yeah, Pepe.
Just a quick question, and again, just because I haven't really seen these, but why is that unconditional QTE the quantity of interest? I mean,
Oh, okay.
it seems so weird. I mean, just like,
Okay.
so what policy problem do you have in mind when you use that as the object of interest?
Okay. First, I agree that you may be interested in that or not. If you have what they call a social utility function or a social welfare function, then with that you can plug in your welfare function here and there, and then you can say if it's a treatment you want or you don't want. Like for instance, if you care about inequality, at the same time you can care about the level, and you have this social welfare function, you take that into account. You find a positive treatment effect, but maybe the variance is increasing, and the positive average treatment effect is maybe not enough to compensate for the increase in the variance. So you want to take that into account, and here you could plug in any. So it will not be, okay, well, it's not a quantitative treatment effect, it will be the difference between the utility function. Actually, the methods I will explain is you will get this CDF of y1, the CDF of y0, and then the results they work for any, I don't know, differentiable, so like differentiable function I think it's a nice way to summarize the effect. Now, well, I have a slide about that. Well, I think quantile treatment effects, they are really nice when you assume rank invariance. And here, it probably makes no sense to assume rank invariance. While with conditional quantile treatment effects, it's easier to assume rank invariance because you have these control variables that make people compare. So I agree that I'm not saying it's obvious we always care about that. But I think it's, okay, so you have the distribution if everyone is treated, this will nobody is treated, so you can see on what is the effect on the aggregate distribution, and it's a way to summarize it. But yeah.
How would you say, if you're saying that, is there any case in which I would look at the, say, distribution of just y1 minus y0 and something about the quantiles?
Okay.
So I guess the annotation would be, would it be reasonable to look ever at the quantile tau of y1 minus y0, everything in parentheses
Yeah.
inside?
Okay, so if you have conditional rank invariance, then you can do that because the conditional quantile treatment effect will be individual treatment effects, and then for each person you estimate the individual treatment effect, and then you can report the distribution of this individual treatment effect. Actually, at some point it was in the appendix of the paper containing the results here, and it was too long. If I remember correctly, it's a special case of the sorted effect in Victor and some other co-authors, I don't remember.
Okay.
But you can do that. You need rank invariance, conditional rank invariance.
Okay, awesome. Yeah. Just like I haven't seen this, and I was just like,
Yeah.
maybe I want to think about like,
Actually, I was hesitating having the bullet point about the distribution of the individual effect. If I remember correctly, I did not put it on the slide, but you can do it. It's also a nice way to summarize the results, but you definitively need conditional rank invariance. Otherwise, yeah, I think it's not interpretable. Well, here you could say it's always the effect on the aggregate distribution. It's not the distribution of the effect, but it's the effect on the distribution.
have you guys ever, like, in this literature, is there ever, like, the possibility that the policymaker can make policy contingent on the value of tau? I mean, I don't know what
Yeah.
I'm just thinking, I mean, these things arise now in the context of personalized
Yeah.
treatment, where you condition on X. So I'm just thinking, is there any instance in which maybe, you know, there would be a reason for why the policymaker wants to think about implementing different policies for different tau levels or something like that?
Definitively. So here is one paper. I don't know what happened here. So last year in Proceeding of the National Academy of Sciences, it's actually a comment, these 3 pages. They comment another paper. And what it's exactly their point is saying, because they are commenting a paper suggesting conformal inference for the individual treatment effect or personalized treatment effect. And they are saying, but actually you can use what you're observing, because for each person you observe either one or the other. We never observe both y0, y1, but one of two, yeah. So this rank invariance, actually we identify individual treatment effect. And then what I do is I say, well, if you take, for instance, the Gaussian copula, and you say, I don't believe in rank invariance, but I think the correlation of this Gaussian copula is at least 0.8, and then you can bound this individual treatment effect and do better personalized treatment assignments. Okay. Where am I? Here. Okay. So now we need this X because we need them to use this conditional independent assumption. And in particular, what the assumption implies, is that the tau quantile of yd, so d can be 0 or 1, so control and treated, you do that separately. The tau quantile of the potential outcome, which in principle is not observable, you can, by the conditional independence assumption, this is independent of the So you can condition on D taking a particular value, 0 or 1, and then once you condition on that, yd is observed and it's equal to y. Okay, so this is conditional independence assumption and this is observation rule. And so this is an identification result saying that the observed tau quantile of y given x and d is equal to the tau quantile of yd given x. So this justifies estimating this one using this result with quantile regression in general, and if you add a parametric restriction, like a linear one for instance here, then you can estimate that with linear quantile regression. But here it's possibly non-linear, but the parametric assumption is linear, so you can estimate that with quantile regression. But this delta tau is not the unconditional quantile treatment effect I mentioned before, it's a conditional quantile treatment effect. So, and now I already said you don't have law of iterated quantile, so you cannot just take this conditional quantile of y. You need to work with something else, and something else is the CDF. Okay? Because the CDF, cumulative distribution function, is an expected value, and so there is a law of iterated CDF if you want. It's trivial application of law of iterated expectation. So, with the conditional independence assumption, the result on the previous slide with quantiles, you can do it with CDF too. So the CDF, yeah, now I see I'm not very, yeah, I'm inverting, I see the notation. But anyway, okay, so the CDF of yd is observed is equal to CDF of y given x and d. So, like I said, CDF is an expected value, so you have a law of iterated expectation. So the unconditional CDF is the expected value of the conditional CDF, so you have the CDF of y given x, that you take the integral of the distribution of x, because we want the CDF of the whole population, so we just take the CDF of x of the whole population, and now using the result here that comes from conditional independence assumption, we can replace the CDF of the potential with the CDF of the observed outcome. And this is something that we can observe and estimate. So, now we have a formula that links the conditional CDF and the unconditional CDF. We have quantile regression that gives us a conditional quantile function, but of course the conditional quantile function is the inverse of the conditional CDF, or the conditional CDF is the inverse of the conditional quantile function. So if you get the conditional quantile function with quantile regression, you invert it, you plug that in here. Here it's the observed covariate distribution, you take the integral, you get the unconditional CDF, you invert again, you get the unconditional quantile function. So there is this link where you start from the conditional quantile function, conditional CDF, unconditional CDF, unconditional quantile function. Okay? Sounds complicated, but you will see it's actually very simple. Yeah.
So heuristically, how because I would think of my quantile regression function, it's minimizing the objective I care about, like even just visually to give me a good linear approximation to the true quantile regression function. But now I'm wondering at the heuristic level, like how good does my estimated quantile regression function need to be so that things don't go crazy when I start, inverting, averaging, and then inverting back. I'm worried that like an approximation error would compound or something like that.
Okay, so you will like one slide. Well, instead of quantile regression, I say let's estimate that directly, and we call that distribution regression. We can do it.
Okay, yeah.
Then it will solve your point here.
Yeah.
Now, what I can say are at least two things. First, if you have a fully saturated model, then using quantile regression, by using quantile regression, you get the CDF in the cell. So it's a non-parametric model. And also another result is if x is continuous and you use a non-parametric quantile regression or a non-parametric distribution regression, they have the same asymptotic distribution. Now the question is about misspecification, and I don't have a good response here. If I have the impression it's the same object, but like if you approximate while the conditional quantile function, you approximate while the conditional distribution function.
Yeah.
But maybe it's wrong, I don't know.
Yeah.
Okay, so I know about that.
So you just described two strategies. One is starting with quantile regression and going all the way to unconditional quantiles of the potential outcomes. The other one that you just responded to Gabe's question with was start from conditional CDF and then go through the rest of the pipeline to get the unconditional quantiles. I'm wondering if you were to go with the first option of doing quantile regression and then inverting the conditional quantile function to get the conditional CDF. Do we need the outcomes to be continuous?
Yes, it's a major difference between quantile regression and distribution regression. Quantile regression you need, okay, it's a little bit more complicated than that. Let me say a few words about that. First, in terms of model, if y is not continuous, I think it's impossible to have a correctly specified model. I mean, except in pathological cases, because if you think about it, you have a line and you try to fit something that has mass points, it's impossible. Like some people have used, this paper, Machado, Santosifa, they use for count data, they use quantile regression, and they add noise. I think there is no reason the conditional quantile will be linear or close to linear. It will be a step function actually. So in such a case, I think you want to use another method, and distribution regression works fine. Then I think quantiles are also interesting for discrete outcomes, but you don't want to impose linearity. So we have a paper where we are interested in these unconditional quantile treatment effects. Why is discrete or has mass points? We use distribution regression in the first step, and you can still report this quantile treatment effect. They still have sort of the same intuitive appeal, I think. But for inference, it's more complicated because it's no longer Adamo differentiable, so it's no longer asymptotically normally distributed. So it's tricky, but I would say you don't use quantile regression if there are mass points or if it's discrete outcome. Yes?
You might have also addressed this when responding to you, but I think I might have missed it. If it's the case that we would need continuous outcomes in quantile regression, but looking at the distribution regression, we don't require that. That difference makes me think that, okay, let me just use distributional regressions throughout. What might be reasons we would want to use quantile regressions over distributional alternatives?
I think maybe in terms of interpretation, so first, even if we report that this is unconditional quantile treatment effect, we still can look at the intermediate step to try to understand how it works. And quantile regression is nice in terms of interpretation, because special case you have the classical linear regression model. So like you estimate for mean square regression, I have the impression we know quite well how to interpret that. Distribution regression, so it's a family of logit or probit. I find more tricky to interpret, and it does not easily, it's difficult to compare. This is first thing. Second thing, it's maybe not a very strong argument, but if you do simulations, and if it's not discrete, it's continuous, quantile regression tend to perform better. So I don't know really why, because non-parametrically it's the same, but different people have done simulations, and we have done simulations, and if you have a continuous outcome, we do better with quantile regression in terms of precision. So it could be a second reason. But I'm fine if, I'm not, I'm fine if you one or the other. Okay, other question? Okay, so here is the algorithm. I more or less said everything. So the first step is use quantile regression. And here, for instance, if you want to have a more flexible model, you do one quantile regression in the control population, or control sample, one in the treated sample, so you get different coefficients here. Then you invert. Okay, so here is one issue, that the estimated conditional quantile function is not necessarily monotone. So when you estimate it, it may go up and down. Of course, asymptotically, it will be increasing. If it's not increasing asymptotically, it means the model is misspecified. Okay. So it's if you want to invert something that is not necessarily monotone, it's not very nice, but you can use this formula here, which is the sample analog of a result you have in the population. So in the population, the quantile function is strictly increasing. So if you, this is one way to invert in the population, and in the sample, this will work. This formula will work even if it's not monotone. So what you are doing is just you estimate all tau. For all taus, you estimate the conditional quantile, and then basically what we do, we count the probability. What is the probability? So we want the CDF at one threshold, lowercase letter y, and here we count the probability or the proportion of quantiles such that the conditional quantile is below or equal to y. And so this, if you take in the population, you get exactly the CDF. A way to look at that is, it's the same if you use Chanuzukov, Fernandez-Valgalichon, or they have a paper about monotonization by rearrangement. It's the same. So I like this formula because here it's a sample analog of something that I explained in the population. Yes?
Do we assume linearity of quantile functions? So we assume linearity of quantile
Here, yes. Here I'm assuming it's a correctly specified model.
for every tau.
Yes. So, yeah. Inference is based on the bootstrap.
No, not about difference, just
Yeah.
it's a very
No, for
small-
consistency, yes. Yeah.
It's because like in the Guillaume lecture we thought about what happened if we're going to specify one quantile,
Yeah.
and here we assume infinite quantile, right?
Yes. Absolutely. So, yeah, there is a price to pay. We need to modelize the whole
Yeah.
distribution. So, I mean, it's still more flexible than having like a conditional distribution. Now, of course, I see all models as approximation, so you want to be flexible, and but there is always a trade-off. Tomorrow we'll talk about inference after model selection. That could apply here. Yeah, that will apply here actually. So yeah, yeah, but definitely here the idea is really we can estimate the whole conditional distribution. Okay, yes.
Just to make sure, when you say that probably monotonicity is you fix x and the function as a function of tau is not monotonic.
Exactly.
That's
Yes.
okay.
Yes. It's exactly right.
So Guillaume mentioned in the morning, so is there a way of imposing that in the estimation explicitly that
Yes.
you want to
Yes.
get monotonicity for the particular tau that
Yes.
you're saying?
Yeah, there are different papers doing that. I think you should know better than me, but if you can impose it on the support of the axis we have, that they should not cross. Personally, for me, it's not a big deal. So in the sense that if it's misspecified, imposing monotonicity maybe can make it even worse. And if it's really, I mean, it should be nice. I mean, if it's so the swing is going up and down, I find it simpler to estimate quantile by quantile. It's faster, and then. But I see the point.
For the other case, when you do it jointly, I mean, how would you take into account the fact that you need information of the beta hat for different taus? So what becomes the objective function in that linear program? So it's not a check function anymore, right? Because that is only for one tau. I'm just having a hard time seeing exactly the structure of what's objective function across constraints. I can understand that in the support of the x's, you just
when this one is, then this, by construction, this one is still increased, or is monotone, this one.
Ah, yes, yes.
And then we integrate, so it's still monotone, and now we can invert without problem this one. Okay, so I explain only this one now. Here, just taking the average, I mean, integrating our distribution of x. If you have a random sample from the population, it means taking the sample mean of the estimated conditional CDF, so it's at a given y, but here it's the average over all the observations you have in your sample. And if you want the effect for the treated, you will keep on your treated here, and so forth and so on. And then this one is monotone, so you can invert it to get the unconditional quantile. Okay, so but probably I'm slow. Okay.
Just one more thing.
Yeah, sure.
Kind of like open question, just I mean, you know, like you guys are doing discussions, but say, if I just think about where the current literature is on estimation of average treatment effects on their own confoundings, right? Just the typical from y1, y0, with conditional on x, we have independence of treatment sign. So say, like maybe 10 years ago or something, this literature would never estimate these conditional distributions of y in x for average treatment effects. Inverse probability weighting would reweight the data. You would need to estimate propensity scores for doing the reweight, but you could do this. So now times have changed, and now there's the double robustness business. So you can do this augmented inverse probability weighting. You estimate these conditional distributions, but you know, the big question is I need to get the influence of the correct influence function to put these things in. So is there a similar discussion in the quantile regression stuff? If you want to get an efficient estimator of this quantile treatment effect, what's the analogous of inverse probability weighting? What's the analogous of double robustness?
It's okay. So I want to say what's inverse probability weighting. It's all the same. So and also it's older than you think. Like quantile treatment effect with inverse probability weighting is 3rd of April 2006, and this is semi-parametrically efficient. And if you do what you are doing here with non-parametric quantile regression, let's say here, it's also semi-parametrically efficient with the same semi-parametric efficiency bound. It's exactly parallel to the results we have for the average treatment effect. And actually, if you think in terms of CDF, it's all sort of trivial because you replace y with indicator function y less or equal to the threshold. So it's not surprising that it's all parallel. So
Well, then why do you say at the beginning that the double ML thing doesn't work? Because if everything is parallel, right? I mean, there's a version of implementing this double machine learning.
okay, so what I said was for quantile regression. For quantile regression, the naive double machine learning doesn't work
Okay.
because the bias will be density weighted. So you need to do this double selection density weighted. But for the unconditional one, actually it's simpler.
Yeah, that's
And there is an earlier paper. So I will discuss these two things tomorrow. But for unconditional quantile treatment effect, it's actually simple in terms of the double selection works. Because you can see that as doing things for the CDF, and the CDF is linear, so it's fine. But conditional quantile regression, it doesn't work at that.
perfect. Thank you.
So yeah, no, just really, so you don't need to do the reordering for Pierre's question, for the answer to your answer to Pierre's question to be, you don't have like a problem when it's near inversion, even if you have crossing and you don't do reordering because of the ordering which you're summing.
This is actually doing the rearrangement.
This does the rearrangement.
Yeah. Because the thing is that, let's say you increase tau, it's going up, and then you increase tau, it's going down, then it's going up again. Here you will sort of count the number that are below, and it's the same as doing the rearrangement. Okay, so we need that here. Here we cannot simply invert that because it's not monotone. Okay, so it sounds very complicated, but actually, so this is the whole implementation in R, and it's for both the treated and the control. Okay? So actually, saying it's very simple, and I did that for 100,000 observations in 2 seconds. Okay, just one regressor, but it's completely feasible and not a problem at all. So what I'm doing here, it's for the treated, so I keep on the treated. I do quantile regression. I do it on a grid. The next slide I explain a little bit, but here I estimate 100 quantile regression on a uniform grid between 0 and 1. If you have not too many observations, you can actually estimate really all quantile regressions. But if you have more than a few thousands, it's computationally becomes difficult. So here 100 quantile regression, and I will explain on the next slide which is this method, but this is very fast. Then here I get the fitted values, so I take just the values of x for the whole population. It's only the fitted here. Here's the whole population. Multiply with the coefficient, what I get is a matrix of fitted values, one row for each observation, one column for each quantile regression. And I do the same here for the control unit, same number of quantile regressions, and here again fitted values for the whole population, so it's for the same, and here is the quantile regression coefficient coming from here. And then the unconditional quantile treatment effect is simply obtained by taking some quantiles, so here I wanted 5 unconditional quantiles, so tau 0.1, 25, 5, 75, 9, and here these quantiles of this matrix minus the quantile of that matrix. Why? Because I have a random sample, so each observation has the same value, and I have uniformly distributed quantiles, so each quantile regression has the same value. So you can treat that as a pseudo sample. It's a way to generate observation if everyone is treated, if nobody is treated. And like I said, so it's all what you need to do. Of course, we have written a package doing that in R and in Stata. But if you prefer to code like I prefer, you will see it's very simple. All these steps, actually, here you have several steps together if you want. At the beginning, I was doing all the steps, but then I saw that it's much simpler than it sounds. One slide about computation. Yes. Absolutely, absolutely. It's my mind. I have two slides about that.
But so for this implementation in R, so this is linear is using LP-solve or whatever CAD solver R has for linear programs, or there.
Okay, so it's
Or how's it?
it's Roger Concar has implemented it's a Barodal Roberts algorithm. Yeah. So but the next slide is about that. Okay. So in print, if you so the package Quantile is great. There are many methods. By default, you get the Roberts-Barodal algorithm, which is a specialization, but he knows much more than I do. A specialization of the simplex algorithm for quantile regression. It works well up to, I don't know, depending on the number of regressors, 5,000, 10,000, 20,000 observations. Then if you have more, there are interior point methods, and if you have even more, you have pre-processing methods. Here, with this method, it's actually an algorithm that uses a pre-processing idea to estimate several quantile regressions. Because the intuition is, it's clear that if you have already estimated the 0.5 quantile regression, and you want to estimate the 0.51 quantile regression, they should be close together. And so actually you can do a one-step iteration, and we can prove that asymptotically it's the same. If you have small steps in tau, you can do one step. But still it's not numerically the same, so some people may think, well, what if you have a mass point, for instance, then the one-step estimator could work not so well. But there is something that is numerically equal, and the idea is the following. You have estimated the median, you know the 0.51 will be close. And to estimate quantile regression, the only thing you need to know is which observations are below, which observations are above the line. So if you estimate the median and you have observations that are clearly below, you know there will still be below the 0.51. Observations that are clearly above, you know there will also be above the 0.51 quantile regression. So you need only to keep observations relatively close to the line, and then you run a new quantile regression with one observation with a big weight for observation below, one observation big weight for observation above, and you keep only the observation close to the line. And you can actually check that the guesses were right. So you get numerically equal results. This is a pre-processing idea that was suggested in Portnoy and Kanker, but they did that for a single quantile You take a subsample, you estimate the quantile regression, then you take the big sample, but you keep only the observation close to the guess, and then you run a quantile regression with a much smaller sample size. Quite an old idea implemented in Quantile. But here what we have done in a paper, we say, well, but let's do that for the quantile regression process. And actually, it's much faster. So even if you have big sample sizes, you start from 1, and then you go down and you go up, and you get the whole discretized quantile regression process. But what I did not say that if you have not too many observations, you can actually estimate all quantile regressions. In R, with RQ, you put tau equal -1, and you get all of them. If you have no regressor, you have n observations, you know there are only n different quantiles. Even if in principle tau is continuous from 0 to 1, you cannot get more than n different values. With quantile regression, it's similar, but it's only of order n times log n. So it's a number of different quantile regressions. And you can actually get all of them by iterating simplex. Yeah, you do just one iteration.
On that, because I want to make sure I understand. So when you say the number of different quantile regressions, it's kind of like, is that the dimension of the grid of the taus? Like how many different values the beta tau function will take?
No.
Or what exactly are you
Okay.
different quantile?
Yeah, I should have started with that. I think that if you have not too many observations, you can actually estimate all of them, and the number is of order n times log n. But quickly, it's too much. This becomes too slow. So instead of doing that, we estimate on a grid. And in the previous example, I had 100 quantile
Grid of tau.
Yeah, exactly, a grid of tau, yes. To prove the results, we need that the grid mesh slowly goes to 0. I mean, slowly.
Absolutely.
Yes, so we need that for
the
the...
n log n, that refers to the number of different points that you need to have in the grid.
No, it's a number of numerically different quantile regressions that exist. So if I give you 100 observations, probably you will get, I don't know, 150 different quantile regression numerically. More you cannot, because actually it's a step function. That there are range of taus that give numerically the same results.
That's what I'm saying. Like this is the different values that the beta tau function can take.
Exactly.
Right? So
Exactly. Yes. But we don't need that for the estimator to work. So for the estimator to work, we can estimate on a grid, and then asymptotically the grid should...
Let me clarify. So I think the reason why I was insisting on the grid is because in my head, if the number of different values that beta tau can take is of order n log n, that tells me that I need to have a grid that at least has at least these values if I want to recover the whole thing, right? Because if I put less values, I'm not going to be able to
Yeah.
get all these jumps,
Yes.
right?
But
So
yeah.
that's why in my head that
But not only that, but you know that on the polytope ratio optimizing, the next slope is not very far. The corner that represents the next slope is not very far. So you can actually one start simplex, and that motivates you to use parallel Robert, even though the problem is large scale, because you're doing exterior point, but you're not walking all around the polytope. You're probably very close to the optimal solution, because the problem is so similar when you just change the quantile. So you both reduce the size by doing the pre-processing, where you fix the size of some of the observation, effectively dropping them from the problem, but you can warm start. And we don't want to warm start into your point method, so.
You know, like, I mean, we have, I mean, Jose is going to come and raise it, but I'm just curious about this problem now that you do it iteratively, and you're
Yeah.
trying to get the whole process, right?
Yeah.
I agree that for one tau it's a linear program, and so it's a polynomial, right? But now you're pasting all these things, and even if you do it smart,
Yeah.
I mean, do we know anything about the complexity of this? Is this NP-hard or is this still polynomial? Because now you're pasting all this grid, and this grid has all these values that are n log n.
Yeah.
Like,
So I think like,
what's the theoretical complexity? Has someone written a paper about that?
I think like in practice, exactly like I said, the number of tiles is not going up so fast, but either if you're doing the path or even just inverting test, so then you have to solve a bunch of quantile regressions. So for inverting the regression of your test, but then like it will be in practice quite a thing to stay with exterior point methods just because you can re-optimize, you can one start. So you don't have to solve from scratch, but especially for the path. For the quantile process, yeah.
Interesting.
Yeah.
Interesting.
But I don't think there's specifically for quantile things like expected theoretical complexity, because are the worst cases, but they're not very representative for LPs in general.
But so here, you see that with a trick here, that even if you have a sample of 100,000, you see the first one, and after that, you work basically with 1,000 observations for each quantile regression. So it's why it becomes very fast. Yes. Someone else has a question. Okay, so asymptotic distribution. Yeah, I will give a sketch here of the asymptotic distribution. You have to look at this paper for formal results. I don't know how much you know. So I have one slide about the functional delta method, because the trick here is we start from a first distribution, asymptotic distribution, which will be the quantile regression coefficient. And they will converge to some Gaussian process that are well studied in the literature, quite old actually. Some result in the 90s and then also beginning of 2000s. And from there, we have the quantile regression coefficient, then we get to the conditional quantile function, which is just the coefficient multiplied. It's a linear function, so it also converges to a Gaussian process. And then when you integrate, now when you invert, it's Hadamard differentiable, which means that we can use the functional delta method. Then when you integrate, it's Hadamard differentiable, we can use the functional delta method. When you invert again, we use again the functional delta method. And then we combine everything with a chain rule. So the formulas are quite complex, but to prove that it's square root inconsistent asymptotically normal is actually applying several times the same tool, which is not so complicated. And for the validity of the bootstrap is the same. Take the functional delta method for the bootstrap. All the clocks are wrong, I think. So there is a functional delta method for the bootstrap, and then you can show like using these same tools that the bootstrap is working. So let's have quickly a look at the functional delta method. So yeah, maybe I would say we need the functional delta method because we are working with functions. So when we invert the conditional quantile function, it's not enough to use one. We need the whole function to invert and then to get a conditional distribution function. So let's call phi the functional of interest. For instance, when you go from the CDF to the quantile function, this is just the inverse function. And so now the question is, what is the asymptotic distribution of phi applied to an estimated function? So CDF and we apply the inverse, and we want to get, so we assume that the CDF is, we assume it can be proved, the CDF is asymptotically normally distributed to the square root n and some Gaussian process. And what we need is Adamov differentiability, which is written here. So basically, it's a uniform differentiability, meaning that it must be differentiable uniformly in H. And then if you have these two conditions, by the functional delta method, you get something that looks like the delta method applied to one monomerial, one vector. And here you get that the asymptotic distribution of the phi function of the estimated f minus the phi function of the true f converges to phi prime, which is the Adamov derivative obtained here, applied to G, which is the asymptotic distribution of f. So let's see an example with the empirical quantile function. So we start from the CDF. The CDF is a sample mean. So the empirical CDF is a sample mean. Empirical quantile is not a sample mean. Empirical CDF is a sample mean. So we can apply the traditional central mean theorem to get that the empirical CDF at one threshold is asymptotically normally distributed, and it's a Bernoulli, it's a sample mean of a Bernoulli, so the variance is CDF 1 minus CDF. Okay. So now we want to go from the CDF to the quantile function, and so what we need is to generalize this result to the whole function, and this whole result, the original Donsker paper, that shows that actually, if you look at this G hat function as a function of y, it will converge to a Gaussian process, which means that if you take any fixed value of y, it's normally distributed, any finite number of fixed values, they are jointly normally distributed, and in addition, the process is continuous, the sample paths are continuous. Okay, so what we have here, it means we have the first part, it's a part here, we have square root n, estimated CDF, 2 CDF converges to some Gaussian process that we can completely characterize. Now we want the quantile to get the empirical quantile function, the distribution of the empirical quantile function. So this phi function is the inverse, you invert the CDF. And now here I give you the result, but intuitively, this is just the formula for the derivative of the inverse function. So the H function here, this is the H that we have here in the notation of Adamov differentiability. And so what we have is, so minus y, because when the CDF gets larger, the quantile function gets lower, and inversely, so you get to minus. And then basically what you get here, it will be the asymptotic distribution of the quantile function evaluated at the tau quantile of interest that we divide by the density. So when you move, if you make let's say you make a small error in the CDF, you want to know what is the effect on the quantile function. So if the CDF is a little bit too large, quantile function will be a little bit too low. Now by how much? Thing is, here the density enters, because if you have a high density, you make a small error in the CDF, it has only a small effect on the, you make an error on the CDF, it has a small effect on the quantile function. Well, if you are in a region with a low density, you make the error in the CDF, it has a big effect on the quantile function. And this 1 over the density evaluated as the quantile function is exactly the right, asymptotically, the right value with which you must multiply the error that you make in the CDF to transform it, to translate it into an error of the quantile, in the quantile function. Yes? In the sense that if you don't put assumptions on the tail's behavior, you have to cut somewhere. Because it's no longer, then you have extreme variability. You can do stuff, but in this paper we did nothing, we cut, and then what we did is that where we cut, we can no longer get the unconditional one, which in principle could be very problematic if x explains a lot. Because if it explains a lot, let's say you have x and y, it explains a lot, then So yeah, in the paper it's more formal where we define these tails, and also the thing is that for the proof you just need to say, well, at some point we cut, and no idea where. So it's yeah, yes.
This prime is the usual derivative, not the function derivative.
It's a functional, it's a Hadamard derivative, yes. But yeah, it's not a proof. You have to look like Van der Waart or other textbooks to get the formally. It's half a page or 1 page to get that formally. Here I try to give the intuition using the inverse of the derivative of the inverse function. And so what you get is asymptotically, for each fixed quantile, you get it's normally distributed. This is a G from the previous slide. So it means this is the asymptotic distribution of the CDF evaluated at this value of y. And then, so basically you get the same as for the it's this one, evaluated at the tau quantile. And then to translate into the quantile dimension, we divide by the density. And this converges to a Gaussian process, so it works also for any finite number of quantiles, but also the paths are continuous. Okay, so this is to show one application of functional delta method. Now, the sketch of the proof with a different step. First, we know that the quantile coefficient, they converge to Gaussian processes. So, first paper showing that, Gutenbrunner and Jouret cover. I think they have some restrictive assumption. Less restrictive, but so we know that. So we have this result. It's not new. Then then we multiply basically with x because we want a conditional quantile function, which is simply that multiplied with x. So it's a linear function of that. It also converges to a Gaussian process. Third step, we invert this conditional quantile function. If it's a continuous outcome, it's also Hadamard differentiable. Functional delta method. It means the estimated conditional CDF will also converge to a Gaussian process for the consistent. Then, and this is a contribution of the paper I cited before, show that the counterfactual operator, what I call the counterfactual operator, is this integral here, where we plug in the estimated conditional CDF, and here it's also, we don't know the CDF of x, so it's the empirical CDF for x. We have a random sample from x, so we can plug it that here and there, and we show that this mapping is also Hadamard differentiable, so we can also apply the functional delta method. So this is the third step. No, it's fourth step, sorry. And finally, once you have the unconditional CDF, we invert again, this is Hadamard differentiable, again functional delta method. And so with a chain rule, we can keep all of them together and we get the asymptotic distribution. Okay, as you can imagine, because of all these steps, the asymptotic distribution is, it's a long formula where you have many things to estimate, like conditional densities, unconditional density, many different objects. Okay. And so instead of trying to estimate that analytically, we use resampling methods. And another thing is we want to make uniform inference. What is uniform inference is inference for the whole function. Okay? So because we do not only care about one quantile, but about the whole quantile function. So what we want confidence bands. This is one function with a minus, another function with a plus. And we want that the probability that the quantile treatment effect, that it could be for any quantile treatment effect, could be for another object, but we want the probability that the true value is inside of the band for all quantiles. Well, actually we cut the lower and the upper end. But in principle, for all quantiles, we want that the probability that the true one is in the band is equal to 1 minus alpha. So it's like a confidence interval, but for a function, and we call that a confidence band. And now, how do we get this confidence band? So first, we decide that, so this is a decision, that this band will be equal to the true one, plus minus some critical value that we will determine in the next bullet point, times the pointwise standard error. Yeah, code. Okay. So okay. So here we have the point one standard error. So okay, I think I forgot to should be divided, I guess. Sorry, it's typo. Should be divided. Okay, so now you see the issue is that we don't know this critical value. If you want to get pointwise confidence interval and you know it's asymptotically normal, then you put 1.96 and you have a 95% confidence interval. But the issue here is that we don't know. We know 1.96 would be good for one quantile, but probably not for several quantiles, and especially not for all of them. So we need something that is larger than 1.96, but we don't know by how much. And this critical value may be different from one case to the other. Because if the quantile confidence are strongly correlated, then actually something a little bit higher than 1.96 will do the job. But if they are like almost independent, if you move a little bit away, then you need a much larger because you are like in a case of multiple testing. And so the solution to that is to resample, to do the bootstrap and to mimic this. So we want to estimate. This critical value, and the idea is this t should be chosen such that the probability that the estimated one, the true one, is in the confidence interval is equal to 1 minus alpha. And the way we do that is we use the bootstrap. And then with the bootstrap you can simulate the distribution. And then we choose the 0.1 minus alpha quantile of the simulated values as a critical value. Yes?
This is a very unfair question, but maybe you thought about that when you were doing this. Is there a way of trying to get uniform bounds directly on the bootstrap resamples? The bootstrap sample? So if I'm doing pointwise estimation, I can estimate the standard deviation on the bootstrap sample, but I can also get quantiles from the bootstrap resamples directly.
For that, we use bootstrap for that.
Yeah, I know.
And we use okay, so I don't understand the
So
question.
if I'm doing it pointwise, I can do the bootstrap,
Yes.
estimate the standard area of my bootstrap draws, and plug in here. And that's what we're doing as a uniform version because you take a sub.
Yeah.
But if I'm doing pointwise, I can also get my bootstrap draws, find the 0.5 and the 0.95 quantiles, and the region between that treat it as a 0.9 confidence interval. Is there a way of doing the latter if I'm interested in getting a uniform bounds?
Okay, I guess I'm still not understanding. So
Can I use directly quantiles of the bootstrap distribution instead of estimating the second moment in the bootstrap samples, even if I want uniform coverage?
for that we use the pointwise bootstrap, and then we use it's like a percentile bootstrap for the test statistic if you want.
Okay. Yeah, right.
So
But could I do a percentile bootstrap on paths?
okay, you can do that on the here it's called Smirnov idea. So we take the maximum deviation over the quantile. So
That's what I understand.
I was lost. Okay, so it's basically inverting the Kolmogorov-Smirnov test statistic.
Yeah.
You could do that for other test statistics, but then it's like percentile bootstrap for this one. And then the advantage of doing that is graphically, I will finish today on that. Graphically, if you have uniform bands, so here you have pointwise confidence interval and uniform bands. So it's a decision that you have taken to inflate the pointwise. There are other ways to do that, but here we have done like that. And the advantage is, let's say you want to test an hypothesis that the contact treatment effect is zero at all quantiles. Here I have my uniform bands. It's enough if I find a single quantile, like this one, where zero is not in the uniform band. So I can reject because the full function should be included, and here I have a value that is not included, so I can reject a null hypothesis that it's uniformly zero, for instance. Or you can test also the hypothesis that is constant. And here it's the same, okay, because here it's, but probably you Of course, if you have a specific null hypothesis in mind, you can try to do better. You can try, especially you can try to generate a bootstrap sample imposing the null hypothesis, you will get a more powerful test. Also, there is no reason that Coleman Smirnov is the best thing you can do. Gramophone misses, other things. So you could think about doing other things.
But yeah, I'm wondering if there's any more brute force in that. If magically all my paths, like when bootstrap showed up, like one on top of the other, they never cross, and I could pick and I had 100 of them. I could pick the fifth and the 95th one, and the two between them would be a uniformly valid 90% confidence band. But of course, they're going to cross all over the place. I'm just wondering if there's a way of directly picking one.
No, I think the way is to define a test statistic and to do that.
Yeah.
But then we know that there is no test statistic that is uniformly more powerful. It will depend on the sort of deviation you want to have power against. And in principle, you could adapt that to the specific deviation you want to consider.
Okay.
You had
I was wondering the same question in another context. I was curious. You'd think that if you have lots of paths, you can construct a set, directly from the paths that would contain 95% of them. And
Since we have infinite computational power to look for a small one.
Maybe I'm misunderstanding that. So what you want to do is say you take bootstrap draws out of let me do it in a grid search. For example, I start with the point-wise 95% critical value for each one of the things, right? And I take a bunch of bootstrap draws and I count how many of the paths that I obtained from the bootstrap were contained in the point-wise maps. And then I see that it's not 95% of them. So I say, gee, I missed it. So I make it a little bit bigger. Now I do again the 95%, and I count, and now instead of 95, I have 98. And no, damn it, it's too much. And then I start doing this bisecting. Right? So you're talking about that algorithm?
So that's when I look, crazy the paths.
That is exactly that.
That is equivalent to the sub-T. I mean, Nicola and I implemented that procedure with what we call like a Bayesian implementation of the sub-T. But it's a paper that I wrote the Applied Econometrics, Journal of Applied Econometrics. But we had some sort of proof that they're first order equivalent. And we did it for Bayesians, but for the bootstrap, I think it's the same. Just because in most case,
Because in like in some cases you want to you have that your bootstrap is going to be validated under weaker conditions if you directly get the quantile of the bootstrap as opposed to estimating moments in the bootstrap samples. So that's why there's a procedure that works directly on the drawn bootstrap sample paths that seem like it would be attractive, but it seems not
this
obvious.
procedure, when we did it, we just did it for this business that, in the context that Bayesian guys, they wanted to have an exact joint confidence region that had exact Bayesian credibility. So we did it this way. We just grid search the critical value, and that just gives you the region. But I mean, in this case, you get the same, no?
It's my impression. Actually, the way you explained was great. I should have explained like that. What you suggest, I'm pretty sure we can construct pathological cases such that it does not work. Because imagine that.
I'm not suggesting anything. I don't know how to do it.
Okay. Okay. My understanding was if you take. No, but okay, it does not work. No, I think it's the best way to. I mean, because if you take pointwise, it will not work because you don't know what is happening.
I mean, if the paths are really well behaved, I can find a tube that contains 95% of the realized paths.
Yeah, but
In the bootstrap, that's going to work, but that's going to be
but
terrible.
if the order is because if the order is not, if the order is changing with tau, then it may be that they all go crazy at one point, and then it will not be valid.
And if they all go crazy at different points, then I'm going to have like the whole screen to be my region. So is there a way to? I don't know. Yeah, that's what I was asking. I don't know how to do it.
So I think it's the closest to what you are suggesting. I think I have to stop, right?
Yeah.
Okay.
I mean, you have a conclusion.
Conclusion, yeah, I don't know. I don't know if some of you are doing applied work, something that is dangerous with quantile regression is you estimate many and then you pick after you have seen the result, and then it's a problem of multiple testing. That should be obvious, but when you see interpretation of results, sometimes it's not so obvious. So it's better if you use uniform bands, you don't have the issue, you are sure you can do that, you can pick quantiles, and you have the honest bands for the whole function. So if the object of interest is a function, you should have confidence band for the function. Okay? So it's the only conclusion I can invent now. But tomorrow I will keep.
Thank you.
Thank you very much.